Let's manipulate the non-rotating terms in the quartic expansion of the ladder operator sum. First, let's have a look at the commutation relation between the ladder operators. I'm going to be using the same condensed notation for the ladder operators that I used in the previous video in the quantum mechanics playlist. When you see a horizontal line at the bottom of the symbol, that denotes the lowering operator. The lowering operator is also known as the annihilation operator. And when you see a horizontal bar in the top of the symbol over here, that denotes the raising operator. And the raising operator is also known as the creation operator. Collectively, they're known as the ladder operators. If we take the commutator in this order, where first we have the lowering operator and then the raising operator, the result is +1. This is implicitly the identity operator. If you act on a state with the identity operator, it has no effect. It does not change the state. But if we swap these two around and we put the raising operator first and then the lowering operator, then we get -1. That's because the commutator is anti-symmetric. So if you take the commutator, because it's the difference, and you swap the two operators in the commutator, you will get a minus sign. So that property is known as anti-symmetry. And these two commutators can be used to define these relationships over here. And we're going to be substituting these red relationships into the terms that I write on this side of the whiteboard. So now let's have a look at the non-rotating terms. Those are all the terms where, in this quartic expansion, where the number of creation operators and annihilation operators is equal. So we have 2 copies of the raising operator and 2 copies of the lowering operator. So let's have a look at all those terms. There are 6 terms in total that have this property. So I'll write them in a special order, which is going to allow us to organize them. First, let's have a look at this term. We have raise, lower, raise, lower. Then let's have a look at lower, raise, lower, raise. After that, we'll have a look at raise, raise, lower, lower, and then lower, lower, raise, raise. And finally, we have 2 more, this final pair, which is raise, lower, lower, raise, and then lower, raise, raise, lower. So these are the 6 non-rotating terms that we got from the quartic expansion. Now you can see that every single one of these terms has 2 copies of the raising operator and 2 copies of the lowering operator. They're just in different orders. And if these operators were commuting operators, we wouldn't have to worry about these commutation relations. This would just be 0 and this would be 0. And then we would just be able to collect all of these guys and put a coefficient of 6 in front of them. We would just have one term with a coefficient of 6. But it's not that simple when these are non-commuting operators. We have a non-commuting algebra over here. So let's manipulate these guys and get them into a standard form that's easy for us to act on a state with. We want them to have the form of the number operator. And the number operator has this form. So I'll write the number operator over here. The number operator has this form. Raising operator followed by lowering operator. And if we have the square of the number operator, that's equal to raise, lower, squared. So these are operators that we know how to work with. We can act with this on a state, and that's going to give us a meaningful result. In fact, it's going to give us how many excitations are in that state, how many quanta of energy are in that state. So this is why we want to express these terms in this form. So we want either raise lower or raise lower squared, because this is just like acting with the number operator twice. And I forgot to put a little power of 2 over here, right? So this is the number operator squared. So this is the number operator by itself, and this is the number operator squared. And when you take the square of an operator, that's the same as acting with that operator twice. So if you act with the number operator on a state, you get how many quanta are in that state, how many excitations above the ground state you have. And if you act with the number operator squared, you get the square of that eigenvalue. So those eigenvalues of the number operator tell us how many excitations we have. Now, what we're going to do is we're going to rearrange these guys, and we're going to put them into a form that consists of these terms. And the way that we're going to use, we're actually going to use this commutation relation, we're going to substitute that in to each of these terms. Now, luckily for us, this first term is already in the form that we desire. This term over here has raise lower, raise lower. That's exactly the same as raise lower squared. So we're already done with this first term. This second term is not in the form that we desire. It is actually in the form lower raise squared. So we have these two squared, but they're in the wrong order. We want to get them in the correct order, and how are we going to do that? Well, we can rewrite this in a slightly different way. We can substitute this relationship over here. And I'll write that in red. That's going to give us raise lower plus 1. So that's equivalent to this over here. So lower raise, that's the same as raise lower plus 1. And we have all of this squared. So that's going to give us raise lower squared plus, we're going to have 2 copies of raise lower when we expand this out. So we have 2 copies of raise lower. And then finally, we're just going to have 1 squared, which is 1. So this is what we get from this term. You can see that we don't just have this term. These 2 terms are not equal to each other. We have these terms, which are residual terms that are a direct consequence of the non-commuting nature of the ladder operators. So another thing I want you to notice about these terms is I've grouped them into pairs. And each of these pairs have the flipped versions of all of the operators. You can see wherever you have a raising operator in this top one, you have a lowering operator, and vice versa. And that's why these guys are paired up in such a way. So this is just a neat way to organize the terms. There's nothing special about ordering them in this specific way. Now let's have a look at this term over here. Here we have raise, raise, lower, lower. So what we can do is we can take these middle 2 guys and we can swap them around. So let's do that. If we take raise and then we swap these middle 2 terms around, so we have to take raise lower, that's going to give us lower raise minus 1. And then we have another lower over here. So that's what we've got. So all I've done is I've taken this raise, that's still over here, this lower, that's still over here, and these middle 2 guys, I've just swapped them around. I've taken raise lower, and I've turned it into lower raise minus 1. That's exactly what we have in this relationship. So now what we can do is we can see that we have raise lower in the first term. So that's the same as raise lower squared. That's what we get from here. And then we have minus 1, we have raise lower. So that's minus raise lower. So we have another interesting residual term over here. But over here we have a minus sign, not a plus sign. So this is a minus residual term. And that comes from this minus 1 when we substitute in the result of that commutation relation. And one thing I want you to notice is you can always collect these guys. You can treat this like a sandwich. You can bring this guy in from the left and this guy in from the right. And that's why you have raise lower, or raise lower squared. And that's the same as this top term over here. Now let's have a look at this term. This is a little more complicated. First, what we can do is we can swap these middle 2 terms, just like we did over here. So I'll write that out. We have lower, and then in these brackets, we'll put the swapped version. Then we have raise, and we'll write this in red. So what do we have in red? Well, we have lower raise, so we're going to have a plus sign. We're going to have raise lower plus 1. right? That's what we have in the top over here. Lower raise is raise lower plus 1. We have a plus 1 over here. And then what we get is if we expand these guys out, we're going to get lower raise, lower raise. That's the same as lower raise squared. So we have lower raise squared. And over here, with this 1, when we bring in the two terms and we treat this like a sandwich, we get lower raise. So that's lower raise. So this looks very similar to what we had up here. We have lower raise squared. And when we expanded this out, we had to swap these guys around first. So let's do that. Let's swap these guys around. That's going to give me, I'll write this in red again. So we're going to have raise lower plus 1. And then I'll close that bracket and give it a square. And then we're going to have another copy of raise lower plus 1. So we have raise lower plus 1. So what is this going to be? I'll write this over here. We're going to have a raise lower squared from this term. So we're going to have one copy of that. Raise lower squared. When we expand this term out, we're going to have two copies of raise lower. But we're also going to have this copy. So that's going to give us 3 copies in total. So we have plus 3 raise lower. And over here, we're going to have plus 1 squared, which is 1. And we also have this plus 1. So that's plus 2. We have plus 2. So that's an interesting residual term. We have 3 copies of raise lower plus 2. So we have this residual term appearing over here. Now let's have a look at these final 2 terms. These final 2 terms are a lot more simple than this term. If we take the last 2 terms over here, we can swap them around. So I'll write that over here. We have raise lower, and then we can swap these last 2 terms around. So lower raise is going to turn into raise lower plus 1. And then what we have is raise lower, that's the same as raise lower squared. And then we also have raise lower, which is just being applied to this 1. And that's going to give us raise lower. And what about this final term? Well, instead of swapping these last 2, we can swap these first 2. And if we swap those first 2, that's going to give us, write this like this, we have raise lower at the end, and we just swap those first 2 around. That's going to give raise lower plus 1. And that looks very similar. That's exactly what we have up here. So we're going to have raise lower times raise lower. That is raise lower squared. And then we're going to have one copy of raise lower. So have a look at all of these residual terms. Every single one of these terms has one copy of raise lower squared. So if we add up all of these guys, we're going to have 6 copies of raise lower squared. And I'll write that underneath. So if we sum all of these guys, we sum all 6 copies, we're going to have 6 copies of raise lower squared. Now, what about the residual terms? Now, if you have a look at the residual terms, there is quite a lot of variety. Over here we have plus 1, another plus 1, another plus 3, then we have a minus 1, a plus 2, and 0 over here. In total, we have 6 copies. So that's 6 copies of raise lower. And we also have plus 1 and plus 2, which is plus 3 in total. So this is the sum of all of these terms. And this is actually what we used in the previous video when we were doing the rotating wave approximation. So when we did the rotating wave approximation, these 3 terms were very important. So when we acted on one of those eigenstates, we got an eigenvalue from here, and we got an eigenvalue squared. So that's when we act with the number operator on one of those states, we just get one eigenvalue, and we get 2 copies of the eigenvalue. We get the eigenvalue squared from this term over here. Now, it is also possible to express this sum in a slightly different way. What I'm going to do is I'll just write this I'll write this underneath over here. I'll factor this 6 out, and I'll write this as raise lower squared plus raise lower, and I'll have this constant 3 over here. So all I've done is factored out this 6. Now, I want you to pay close attention to this term over here, raise lower squared. Now, what we can do with this raise lower squared is I'll write all of this stuff in this corner over here. If we pay attention to this term and this term, we can see that they're very similar. The only difference is that these middle two guys are swapped around. Over here we have raise, lower, and over here we have raise, lower, lower. We can take this term over here, and we can write this as raise squared, lower squared. So this term is actually equal to raise squared, lower squared. And another way of looking at it is you can take this term and you can swap these middle two around. So I'll write that over here. If we write raise lower, and we swap these middle two, we just isolate these middle two and we swap them around, that's the same as raise, and the result of this is equivalent to this. Raise lower plus 1, and then you have lower. And if you expand that out, that's going to give you raise squared, lower squared, plus raise lower. Now, do you see the reasoning behind this? All we've done is we've applied that sandwich technique again. And that's given us raise, which is raise squared, and then lower, which is lower squared. And then we have this residual term of raise lower. So this, if we move this term to the other side, we make it a minus, is actually what we have in this expression over here. Can you see that? See that relationship? We have a minus over here and a plus over here. That's because we're just moving this to the other side of the equation. So now what I want to do is I want to consider this term over here. What is this equal to? So I'll write this in a different color. If we consider raise lower squared plus raise lower, that's what we have inside over here. We can rewrite this raise lower squared in a slightly different form. We can see that raise lower squared, in fact, I'll write this very explicitly up in the top over here, because what we have down here is equivalent to this, we can write this as raise squared, lower squared, plus raise lower. So this is analogous to this relationship. We just have a plus sign instead of a minus sign. Now we can substitute this relationship into this relationship over here. So raise lower squared is equivalent to this. And that means that we can write this in an equivalent form that is equal to raise squared, lower squared, plus 2 copies of raise lower. So one copy of raise lower is already here, and another copy of raise lower comes from substituting this relationship over here. So that is that residual term from swapping over these guys around, because the commutator is not equal to 0. These are non-commuting operators. Now that we have this relationship, we can substitute this inside this expression over here. So let's do that. So we're going to have, this is equal to 6 times, we have raise squared, lower squared, plus 2 copies of raise lower, and then plus 3. We can expand this out. That's going to give us 6 raise squared, lower squared, and then we're going to have 12 copies of raise, and I'll explicitly write this as raised to the power of 1, lower to the power of 1, and then we have 3 raised to the power of 0, lower to the power of 0. So the terms over here all add up to 0. So the superscripts, the powers of these ladder operators, they add up to 0. These ones add up to 2. These ones add up to 4. So in a quartic expansion, you would expect that all the terms have these exponents adding up to 4. But these guys are the residual terms. They are a consequence of the non-commuting nature of these ladder operators. This residual term is raised lower. So this will give us eigenvalues. This term over here doesn't have any copies of the raising and lowering operators. So when we act on this on a state, it's just going to be the same as multiplying by a numerical constant. So this is just a numerical constant. And if we put this into a Hamiltonian, we can actually neglect this term because the constant doesn't make any physical difference. There's no physical significance to changing the zero of the potential energy. It's exactly the same concept. So what do we have over here? We have all of these terms having the same exponent. That means if you take the difference of the exponents, all of these guys are going to give 0. That is why these guys are called non-rotating terms. So these are the non-rotating terms that we actually used in first-order perturbation theory when we were describing the transmon Hamiltonian. So we treated the transmon Hamiltonian as a harmonic oscillator with a quartic perturbation. And the only terms that contributed to that quartic perturbation in first-order perturbation theory were these terms over here, the non-rotating terms. And you can also think of this in terms of the rotating wave approximation. All of those rotating terms that have non-zero differences for these exponents, they were thrown away and weren't considered. Only these terms were considered for the rotating wave approximation. So now you've seen all of the algebraic details that go behind the expression that was used in the transmon Hamiltonian video. So hopefully that was useful. We'll do some more algebraic work with these ladder operators in later videos in the quantum mechanics playlist, which you can find if you click over here.